Think about those massive construction projects you see taking shape. A new bridge, maybe a sprawling hospital. They can look like, well, organized chaos, right?
Ah, yeah, they really can.
But underneath all that activity, there's actually a meticulously planned timeline, a kind of roadmap that aims to keep everything synchronized.
Exactly. It's the foundation, really, the foundation upon which any successful construction project is built.
Right.
Without a robust schedule, you're just asking for delays, budget overruns, and honestly, a whole lot of headaches trying to coordinate different teams and deliveries. It gets messy fast.
So our goal today is to really dig into the nuts and bolts of creating one of these master construction schedules. We've got a great resource, Chapter 22, titled Creating and Using the Schedule. Looks like it's from a leading construction management guide. And our mission, essentially, is to uncover how a contractor approaches planning a project. From the initial groundbreaking right through to the final touches. We want to try and get inside their head a bit.
And it's way more than just listing the big milestones, like foundation complete. A truly effective master schedule dives into the day-to-day tasks.
Okay.
It covers those critical milestone achievements, sure, but also the logistics, often really complex logistics of getting materials on site, and even all the necessary administrative stuff like permits and inspections.
That was a holistic view.
It has to be. It really ties everything together.
Okay, let's unpack this then. Our source material, this Chapter 22, it breaks down developing a master schedule into 5 fundamental steps.
Right.
It starts with identifying all the individual work activities, the tasks.
Yeah.
Then figuring out the logical order they need to happen in the sequence.
Makes sense.
Followed by estimating how long each of those activities will actually take.
The duration, yeah.
And then, interestingly, there's a distinct step listed for hand drawing the schedule before it even goes near a computer.
Ah, yes, the old school way, still very valuable.
And then finally, step 5 is inputting all that data into scheduling software.
That's the sequence. And that first step, identifying the work activities, it's absolutely crucial. It's not just like a random brainstorming session either.
No.
No, it's a structured process. It uses something called a work breakdown structure, or you'll often hear it called a WBS.
The WBS, got it. So what exactly is that? And, what makes it such a vital tool?
Okay, imagine the whole project is like a giant jigsaw puzzle. The WBS is like sorting all those puzzle pieces into smaller, much more manageable groups based on what part of the picture they belong to. It's basically a hierarchical breakdown of all the work that's required.
Okay, breaking it down.
Yeah, and its main goal is to organize and, importantly, control all those individual tasks within a really clear framework. Now, the level of detail you go into, that really depends.
Depends on what?
Well, how complex the project is, for starters, how much of the work you're planning to subcontract out, and also just how tight a grip the main contractor wants on the day-to-day progress.
That makes perfect sense. I mean, building a garden shed isn't going to need the same WBS detail as, say, constructing a multi-building university campus.
Exactly. Spot on.
Now, within this WBS, we have these activities. What specifically defines an activity when we're talking about a construction schedule?
Good question. Think of an activity as like a mini project within the larger project. It has a duration. It takes a certain amount of time to complete.
Okay.
It consumes resources, could be labor, equipment, materials, even money. And importantly, it has a clearly defined scope of work, something specific like install insulation in exterior walls, or maybe pour concrete for the loading dock.
Right, something tangible.
Yeah, exactly. Each activity has a distinct start and a distinct finish. And critically, you need to be able to measure its progress to know if you're actually on track.
So we're talking about these discrete, measurable tasks. Our source mentions the CSI master format as maybe a broad initial way to categorize things. Concrete, masonry, electrical. But it also emphasizes that for practical scheduling, you usually need to get much more granular than that, right?
Oh, absolutely. Those broad master format categories, they're a decent starting point for just organizing your thinking, maybe structuring the WBS initially, but they definitely lack the precision you need for effective day-to-day scheduling.
How so?
Well, take electrical, for instance. That could cover everything from running conduit deep inside concrete slabs to, installing the final light fixtures months later. Each of those subtasks needs its own place in the schedule.
Okay.
They'll have their own duration, their own specific resource needs, and their own dependencies on other activities. You can't just lump them together.
And the chapter gives that great illustration with a simple garage project. Just having one big activity called complete garage spanning several weeks isn't very helpful for managing it.
Not at all.
But breaking it down into, say, order and deliver lumber, then excavate for foundation, then pour foundation walls, that gives you much more actionable steps, things you can actually manage and track.
Exactly. And you can keep breaking those down further if you need to. Pour foundation walls might break down into set forms, place reinforcing steel, and then pour concrete.
Right.
The key is finding the right balance, really. You need enough detail to accurately track progress and coordinate your subcontractors effectively. But you don't want to get bogged down in so much minutia that the schedule itself becomes unwieldy. Like the chapter says, you don't need an activity for hammer every single nail.
Right, yeah. You definitely lose the forest for the trees there.
Yeah.
The source also makes a really valuable point about often separating activities by trade.
Ah, yes.
So instead of just one big plumbing task for the whole project, you might break it down into rough plumbing under the slab, then maybe rough plumbing in the walls, and finally plumbing fixture installation. That seems like it would massively streamline coordinating the different subcontractors.
Oh, it makes a huge difference. Absolutely. It lets each subcontractor focus really clearly on their specific deliverables, and it makes it much, much easier for the superintendent or project manager to track their individual progress.
Okay.
And, as the chapter points out, you might even have different levels of WBS detail, maybe a summary version for high-level oversight for the superintendent and maybe the client.
Right.
And then a much more detailed version used internally by the project team for that day-to-day management and close coordination.
Okay, so we've identified all the individual work packages using our WBS. Now comes the logical next step, figuring out the sequence, the order these activities need to happen in.
That's right. This is called task sequencing, and it's really all about understanding the dependencies between different activities.
Dependencies.
Yeah. Most tasks, with the obvious exceptions of the very first thing you do, like mobilize and the very last thing, like final cleanup will have activities that need to be completed before they can start. Those are their predecessors. Yep. And they'll usually have activities that follow once they're done, that those are their successors.
And as we touched on, some of these sequences are just, well, common sense, aren't they? You can't put the roof on before you've built the walls.
Pretty fundamental, yeah.
But I guess in more complex projects, contractors often have choices about how different activities link up. And the goal is to find the most efficient and logical flow to hit that overall project timeline.
Absolutely. There are several factors that drive these sequencing decisions. The natural sequence is definitely one you just physically can't do certain things out of order.
Right.
But you also have to consider which activities can run concurrently, happening at the same time. For instance, maybe you can start ordering long lead items like windows while the foundation is still being poured or cured.
Okay, doing things in parallel.
Exactly. Efficiency and cost also play a big role. Maybe sequencing tasks in a particular way lets you use one expensive piece of equipment, like a crane, for multiple tasks back to back, saving time and rental costs.
Safety must be a huge consideration here too, I'd imagine. You wouldn't want different crews working in a way that puts them at risk from each other's activities, like working directly underneath another crew.
Definitely. Safety is paramount. And the physical limitations of the site itself can also dictate the sequence. You might just not have enough space for multiple large crews to work effectively in the same area simultaneously. And sometimes, it really does come down to the contractor's preferred methods. They're tried and true ways of tackling certain types of work based on their experience.
So it's a real mix. A mix of what must come first, physically, and what makes the most sense to come first for efficiency, cost, and safety. The chapter highlights the importance of identifying immediate predecessors and successors. Why is that level of specificity, that word immediate, so critical?
Right. The word immediate is key there. Think about it. While the foundation absolutely has to be in place before you can install flooring on the ground level, the foundation isn't the immediate predecessor to the flooring installation itself. The immediate predecessor might be something like the concrete slab being fully poured and cured, maybe even screeded level.
I see. The very next step.
Exactly. Understanding these direct one-to-one dependencies is absolutely essential for building a schedule that accurately reflects the reality of how the construction process unfolds. You need that direct link.
Right. You're mapping out those very direct relationships. And this whole process, figuring out the order of activities and how they connect, that's what the chapter refers to as job logic, isn't it?
That's the term, yeah. The job logic is basically the underlying framework. It defines how all the different pieces of the project puzzle fit together in time.
Okay.
And once you've established that logic, figured out those dependencies, the next crucial step is to estimate how much time each of those individual activities is likely going to take. You're assigning durations.
Duration. Okay, that seems straightforward enough on the surface. It's simply the amount of time needed to complete an activity. But the chapter points out that for these master schedules, durations are typically expressed in days.
That's generally the standard, yeah. Because for most activities you track on a master schedule, a day provides a pretty useful level of granularity.
Not too broad, not too narrow.
Exactly. Thinking in weeks is usually too broad for effective control, and tracking every single task in hours would just be incredibly cumbersome and probably unnecessary for most things.
Makes sense.
However, as the chapter does note, there are exceptions, particularly for very high stakes or extremely time-sensitive activities, or maybe when you're dealing with very expensive equipment like a massive tower crane. In those cases, even hourly tracking might be critical for cost control and optimization.
Okay. So, how do contractors actually go about estimating these durations? It can't be an exact science, surely. There must be a degree of informed guesswork involved.
It's definitely an estimate, you're right. But it should be an informed estimate. It's typically based on a combination of factors and, crucially, experience.
Like what factors?
Well, the overall project timeline you have to work within, for one, the resources you expect to have available, the size of your crews, the availability of key equipment, and, of course, the expected productivity rates for those resources. How much work can a typical crew get done in a day?
Right.
And contractors, especially experienced ones, often lean very heavily on their past experience with similar types of projects. Plus, the knowledge of their seasoned foremen and superintendents is invaluable here.
The source mentions a practical approach.
Yeah.
Sometimes working backward from the required completion date and sort of blocking out time windows for different major phases. That sounds like a good way to get a high-level view initially.
It can be, yeah. It helps frame the overall timeline.
And it also emphasizes the importance of talking to the subcontractors, getting their expert input on how long their specific portions of the work will realistically take.
Oh, that collaboration with the subs is absolutely vital. They're the specialists in their trades, right?
Yeah.
Their insights into how long specific tasks will take, given the project's unique conditions, are invaluable for creating a schedule that's actually realistic.
But even with all that careful consideration and collaboration,
They're still estimates, exactly. As the chapter wisely points out, these durations can be influenced by a whole host of unforeseen factors. Things like unexpected bad weather, discovering weird conditions on site, maybe changes in the project scope requested by the owner, or even just normal variations in crew productivity day to day.
so you build in some contingency, or just accept it's an estimate.
A bit of both, usually. You try to be realistic, maybe slightly conservative on critical items, but you also know you'll need to manage deviations as they happen.
Okay, so we've got our list of activities from the WBS, we've figured out the sequence, the job logic, and we've got our best estimated durations for each task. Now comes that step that really stood out to me, hand-drawing the schedule. In our super digital world, why is physically sketching this out still considered such a valuable step?
Yeah, it might seem a bit old school, maybe even quaint to some, but there's a real power in that manual process, especially for the person developing the schedule initially.
Oh, so?
Well, it forces the contractor, or the scheduler, to really visualize the entire flow of the project, to physically connect those activities with lines and arrows representing the dependencies. This hands-on approach can often reveal logical inconsistencies or maybe overlooked dependencies that might not be immediately obvious when you're just typing data into rows and columns on a computer screen.
Ah, so it's like a mental check.
Exactly. The software is an incredibly powerful tool for calculation and analysis, don't get me wrong.
Yeah.
But it fundamentally relies on the accuracy and completeness of the logical information you feed into it. It can't spot a flaw in your thinking.
So the hand-drawing step is a way to catch potential oops moments, those logic gaps, before they become actual real-world problems out on the construction site.
Precisely. It's a valuable review step.
The chapter specifically mentions activity on node diagrams, or AON, as being the easiest type to sketch out by hand. Can you explain briefly how those work?
Sure. In an activity on node, or AON, diagram, each individual activity is represented by a shape, usually a circle, or maybe a square or rectangle. That's the node.
Okay, a box for each task.
Right. And then these nodes, these boxes, are connected by arrows. An arrow going from, say, activity A's box to activity B's box signifies that activity A must be completed or sometimes reach a certain stage of completion depending on the specific link type before activity B can begin.
So the arrows show the dependency.
Exactly. These visual connections directly represent the job logic, those predecessor-successor relationships we talked about earlier.
And by physically drawing these connections, maybe on a big piece of paper or a whiteboard, the contractor is really forced to think through the optimal sequence, the best flow for the project.
That's the idea. The source mentions they usually draw it generally from left to right, kind of representing the flow of time, often building it up layer by layer, maybe starting with foundational tasks at the bottom or left and moving towards completion activities at the top or right. And you always have a clear start node and a clear finish node for the entire project.
It becomes a visual map of the project timeline.
Exactly. It's a tangible way to see the project timeline and, crucially, the interrelationships between all the tasks unfold visually. There are also some general conventions used when creating these network diagrams.
What's this?
Well, for instance, with the exception of that very first start activity and the very last finish activity, every other activity or node should ideally have at least one arrow coming into it, a predecessor, and at least one arrow going out of it, a successor.
Everything's connected.
Right. Each node represents a single, distinct activity. And, as we mentioned, the basic assumption is that an activity generally can't start until all its preceding activities, the ones with arrows pointing to it, are complete.
Okay.
It's also worth noting that these hand-drawn diagrams usually aren't drawn perfectly to scale in terms of time. The length of an arrow doesn't represent duration. The main focus is just illustrating the logical dependencies clearly. And you generally read the flow of work from left to right and sometimes top to bottom.
Figure 22.2 in our source material provides a simple but really effective example. It shows activities labeled A through F, and it clearly indicates the predecessor for each one with arrows. It really illustrates how concurrent activities have those that can happen at the same time, like A and B in their example, branch off from their shared predecessor. It makes those dependencies very easy to visualize.
Precisely. By visually mapping out those connections by hand, you can often spot potential bottlenecks, or maybe areas where the logical flow isn't quite as efficient as it could be, much easier than just looking at a list.
Makes sense.
And once the contractor or the scheduler feels pretty confident in this hand-drawn network diagram, they've worked out the kinks in the logic, then the next step is to translate all of that information, the activities, the durations, the dependencies, into the scheduling software.
And this is where the digital tools really come into their own, I suppose. The chapter mentions that these software programs are incredibly sophisticated now. They can display the schedule in all sorts of different formats with varying levels of detail,
They're very flexible.
which allows contractors to tailor the view for different stakeholders, maybe a high-level summary for the owner, a detailed look-ahead for the superintendent, that sort of thing.
Exactly.
Gives examples like Oracle's Primavera P6, which you often hear about for really large, complex infrastructure projects.
Right, the industry standard for big stuff.
And then Microsoft Project, which it suggests might be more common for smaller to medium-sized builds, maybe emphasizing its relative user-friendliness or lower cost.
Both are powerful tools, just aimed at slightly different scales sometimes. These software packages take that raw data, the list of activities, their estimated durations, and critically, the logical links you've defined, and they can generate all sorts of useful outputs.
Like gap charts.
Detailed Gantt charts, yes. Network diagrams that are much cleaner and more formalized than the hand-drawn versions. And they perform a whole range of analyses, including identifying that all-important critical path we'll talk about.
Okay.
Plus, they make it much, much easier to make adjustments as things change, track progress against the original baseline plan, and generate reports for project stakeholders.
Now, up to this point, we've mostly been talking about that basic finish-to-start relationship, haven't we? Where one task has to be completely finished before the next one can begin, like digging the hole before planting the tree.
That's the most common one, yeah, FS linkage.
But the source points out that it's not the only way activities can be linked. There are actually other types, start to start, finish to finish, and even start to finish. Can you maybe unpack the nuances of those different linkage types for us?
Sure. So, besides finish to start, FS, you have start to start, or SS. This link means that two activities can begin more or less at the same time, Or perhaps the start of the second activity is dependent on the start of the first one, maybe with a small lag.
Okay, starting together. Example.
A good example from the chapter is, the moment you receive the official notice to proceed on a project, you can probably also kick off your initial project management and administrative setup tasks. Their starts are linked.
Got it. What about finish to finish? FF.
Finish to finish indicates that the completion of one activity is dependent on the completion of another. They need to finish around the same time, or one can't finish until the other does.
Example.
Let's see. Maybe finalizing the project punch list, the list of final fixes. That might not be able to be officially completed until all the individual construction trades have also fully completed their own final touch-up work. Their finishes are linked.
Okay, that makes sense. And the last one, start to finish. SF. That sounds a bit counterintuitive.
It's definitely the least common type of linkage, but it does exist. Start to finish means that the start of one activity essentially forces or triggers the end of another activity.
Okay.
The example used in the chapter is pretty good. The actual start of a store's grand opening event signifies the planned end of the main advertising campaign that was leading up to it. The start of the event stops the ads.
Okay. I can see how that works. So understanding these different types of dependencies, FS, SSF, SSF, seems pretty crucial for creating a schedule that really accurately and realistically reflects how work actually happens out on a construction site. It's not always just one thing after another.
Exactly. Using the right type of linkage gives you a much more nuanced and realistic picture of the field operations.
Now, one of the most vital concepts in project scheduling that the chapter introduces, you mentioned it earlier, is the critical path. It sounds very important just by its name. What exactly is it?
It is extremely important. The critical path is, essentially, the sequence of linked activities in your project schedule that determines the shortest possible time the project can be completed in. Or, put another way, it's the path with the longest total duration through the network.
The longest path dictates the shortest time. Explain that.
Because every activity on that longest path has to be completed in sequence. If any single activity on this critical path is delayed, even by 1 day, it will directly cause a delay in the overall project completion date, unless you can make up time elsewhere later on that same path.
Okay, so it's the bottleneck path.
That's a good way to think of it. Every project has at least one critical path, and sometimes, especially in complex projects, there can be multiple critical paths running concurrently through different sequences of activities.
And the network diagram that you create, either by hand or more likely in the software, can visually highlight this critical path for you, right?
Yes, absolutely. Typically, the scheduling software will automatically calculate and identify the critical path. The activities that make up the critical path are usually highlighted, maybe shown in red, or with a bolder line in the network diagram view. Figure 22.4 in our source shows a simple example.
Right, I see that. It shows 3 different sequences of linked tasks, like 3 possible routes from start to finish. Each path has a calculated total duration based on the durations of the tasks within it.
Correct. And the critical path is simply the one with the longest calculated duration. In that specific example diagram, it's the path going through tasks 1, 2, and 3, which adds up to 9 days. The other paths are shorter.
So any delay on task 1, 2, or 3 in that example will push back the entire project finish date beyond those 9 days. The chapter also introduces the related concept of float. How does float relate to the critical path?
Float, sometimes also called total float or slack, is the amount of time that a particular activity can be delayed without impacting the overall project completion date.
So it's like buffer time.
Exactly. It's wiggle room. Now, activities that are on the critical path, by definition, have 0 float. There's no buffer. If they slip, the project finish date slips. But activities that are not on the critical path typically have some amount of positive float. This means they could start a bit later or take a bit longer than originally planned, up to the amount of their float, without actually delaying the final project completion. That gives you some flexibility in managing those non-critical tasks.
So identifying the critical path is absolutely essential, isn't it? Because it pinpoints exactly which tasks need the most careful monitoring and the tightest management to keep the entire project on schedule.
Absolutely. That's where the project manager's primary focus often needs to be managing those critical activities.
And the software, as you said, can calculate all of this for you automatically. It can determine the critical paths, calculate the earliest and latest possible start and finish dates for every single activity, and tell you exactly how much float each non-critical task has.
Yes, the computational power is immense.
But the chapter also touches on an interesting point, maybe a bit philosophical.
Yeah.
The debate between relying solely on the software output versus also having a deeper, maybe manual understanding of how it's calculated.
That's a really insightful point they make. While the software undoubtedly speeds up the process incredibly and can handle schedules far more complex than you could ever manage manually,
Right.
some seasoned project managers still argue that truly understanding the underlying calculations and the logic behind why certain activities are critical, perhaps even by manually calculating the critical path on your hand-drawn diagram for simpler projects, gives you a much deeper appreciation for the dynamics of the schedule.
So it's not just accepting the computer's answer.
Right. If you understand why those activities are critical, how the durations and logic interact to create that path, you're arguably much better equipped to make smart, informed decisions when unexpected issues inevitably arise during construction. It's about understanding the engine driving the schedule, not just reading the fuel gauge on the dashboard.
That makes perfect sense, having that intuitive grasp of what's truly driving the schedule.
Yeah.
Now, a construction schedule, as we've hinted, isn't some static document that you create at the beginning and then just file away, is it? Things are constantly changing on a dynamic construction site. So updating the schedule must be a crucial ongoing process.
Oh, absolutely. Critically important. The schedule is a living document. It needs to be regularly updated to accurately reflect the actual progress being made out on site. If you don't update it, it quickly becomes useless as a management tool.
So how does that updating process work?
It generally involves comparing your original baseline schedule, that's the initial plan you created, with the original plan start and finish dates for all the activities.
The snapshot from day one.
Exactly. Comparing that baseline against an updated schedule that shows what work has actually been completed to date, what activities are currently in progress, and what's still remaining. Importantly, the baseline schedule itself remains unchanged throughout the project.
Why is that?
It serves as a historical record, a benchmark of the initial intentions, which is vital for tracking deviations, analyzing delays, and potentially for contractual claims later on. It can be as simple as a basic bar chart just outlining the original plan, like in figure 22.5 for the garage project.
Okay, so the baseline is fixed, and these updated schedules visually show the progress. The chapter mentions how software like Microsoft Project often uses things like split bars within the Gantt chart to indicate how much of an activity has been completed.
Yes, the software uses various visual cues. Split bars are common, where part of the bar is filled in to show completion. Sometimes different colors are used, or percentage completion indicators are displayed right on the bars. It makes progress easy to see at a glance.
And figure 22.6 in our source provides a clear example of an updated schedule for that same garage project. It shows progress as of a specific date, April 8th. And you can see where a delay, in this case, the delivery of bricks was late, has had a knock-on effect.
Exactly. You can see how that brick delivery delay has pushed back the subsequent tasks that depended on it, like laying the brick. And because laying the brick was likely on or near the critical path, it ultimately impacts the overall projected completion date for the garage. The software automatically recalculates all these dependencies and the critical path based on the reported progress and any changes or delays entered.
It's really quite incredible how it can track all those interconnected changes and ripple effects and forecast their impact on the overall timeline. And it's not just about tracking dates and progress, is it? The chapter mentions that this same software can often be used to track costs associated with different activities, maybe manage equipment allocation, and even keep tabs on administrative procedures like inspections or submittals.
That's right. The schedule can become, and often should be, a central hub for managing a whole wide range of project-related information, integrating time, cost, and resources.
And for many projects, particularly larger ones or those that are publicly funded, submitting an updated schedule along with your monthly payment request is often a standard contractual requirement, isn't it?
Very common, yes. It shows the owner or client that progress is being made according to plan, or it documents any delays and their impacts. But beyond just contractual requirements, many proactive contractors find it really beneficial to update their schedules even more frequently.
How often?
Maybe weekly, especially during busy phases, or even daily for very fast-paced or critical parts of a project. The goal is to always maintain a clear and accurate picture of exactly where they stand relative to the plan.
Now, one of the practical challenges they highlight in the source is accurately determining how much of a particular activity has actually been completed when you're doing these updates. Just saying, oh, we're about 50% done, might not always be a reliable indicator, right? Especially if the remaining 50% is significantly more complex or time-consuming than the first half.
That's a very real challenge. Percentage complete can be subjective. The chapter suggests that perhaps the most common objective method is to base progress on the physical quantity of materials that have been installed or put in place.
Okay, like measuring progress based on output.
Exactly. Tracking progress based on, say, cubic yards of concrete poured, or the number of linear feet of pipe installed, or square feet of drywall hung. It's tangible and measurable.
But even that has limits.
It does. As the chapter astutely points out, this method still has its potential limitations. You might have physically installed, say, 80% of the total length of ductwork, but maybe the remaining 20% involves all the intricate final connections, balancing dampers, working in really tight, awkward spaces. That remaining 20% might actually take just as long or even longer in terms of effort and time as the first 80% did.
So the physical quantity doesn't always equal the effort remaining.
Precisely. So experienced project managers often use a combination of metrics to get a more comprehensive and realistic understanding of the true progress. They might look at physical quantities installed, but also factor in estimates of the remaining duration needed, or perhaps even track the labor hours expended compared to the budgeted hours for that task.
Using multiple lenses to gauge progress.
Exactly. And our source material actually encourages listeners who want to go deeper on this to review Chapter 20, which apparently explores in even greater detail how these schedules are used for actively monitoring, evaluating, and controlling projects throughout their entire life cycle.
Good tip. Finally, the chapter concludes with a really useful glossary of all the key vocabulary we've touched on today. Terms like activity on node, critical path, float, job logic, and that fundamental work breakdown structure, or WBS.
Yeah, that's a helpful summary.
It seems like a great way to reinforce the essential language you need to understand and talk about project scheduling effectively.
Absolutely. Having a solid grasp of these core terms is really fundamental to understanding scheduling concepts and discussing them intelligently.
So just to recap our deep dive today, we've really explored the systematic, step-by-step process that contractors use to create a master construction schedule. We started with breaking down the entire project into manageable activities using the WBS.
Identifying the work.
Then logically sequencing those activities, figuring out the dependencies and the job logic, then estimating their durations, often incorporating that surprisingly valuable step of hand-drawing a network diagram, usually AON, to catch early logic errors.
That critical thinking step.
And then finally, using sophisticated scheduling software to input the data, refine the plan, analyze it, and crucially, continuously update the schedule as the project progresses.
You're right.
We also unpack the different types of activity linkages beyond the basic finish to start and drill down into the critical importance of identifying and understanding the project's critical path and the related concept of float.
And I think what becomes really clear through all this is that this level of detailed planning isn't just some administrative burden or paperwork exercise. It's absolutely fundamental. It's a core tool for managing the inherent complexity of construction projects.
Yeah.
And maybe most importantly, for proactively identifying and addressing potential roadblocks or issues that could otherwise lead to really costly delays and budget problems down the line.
You know, this whole process, thinking in terms of breaking things down, identifying dependencies, estimating durations, finding the critical path, it really makes you think, doesn't it? Even if you're not in construction, how could you apply this kind of structured thinking to your own multi-step projects, whether that's at work or even in your personal life?
That's interesting.
What might be the critical paths in your own endeavors? You know, those specific sequences of tasks where a delay in just one step could have a kind of domino effect on your overall goals or deadlines.
That's a really powerful question to reflect on. Perhaps by consciously applying some of these principles, breaking down our own projects, big or small, into smaller activities, really thinking about their dependencies, maybe even sketching out a simple flow, and identifying those sequences that are absolutely critical to the end result, maybe we could all gain a new level of clarity and maybe even control over our own timelines and outcomes.
It's definitely food for thought. Well, if this deep dive into the world of construction scheduling has sparked your curiosity, there are certainly a wealth of resources available out there to explore these project management concepts in more detail.
Oh, absolutely. It's a huge field.
It really is a fascinating discipline with tools and techniques that, as we've just discussed, can be surprisingly applicable in a really wide range of fields, far beyond just building sites.